So welcome everyone. To the Computability Theory Applications seminar. So we're very happy today to have Takayuki Kihara, and he will tell us about Lawvere-Tierney topologies for computability theorists.
Yes, thank you for the introduction. Today, I'm going to talk about Lawvere-Tierney topologies for computability theorists. So I first explain what Lawvere-Tierney topology is. Lawvere-Tierney topology is a notion in topos theory, but in this talk, so we will consider this concept only for the effective topos. The effective topos is a kind of topos which is introduced by Martin Hyland. And then we point out that there is a surprisingly deep connection between Bayer of degrees in computable analysis and Lawvere-Tierney topology on the effective topos. So in particular, this connects computability theory and topos theory in a certain sense. So of course, we consider Lawvere-Tierney topology on effective topos. So it's no surprise that this is related to computability theory, but the non-trivial point is that Lawvere-Tierney topologies on the effective topos is not only computability theoretic, but also degree theoretic. And surprisingly, it's deeply related to Bayer of degrees. Okay, so I first explain what the effective topos is. So the definition is very complex. So I want to give a detailed definition here, but just to give a general idea of what it is. So it's a kind of the world of computable mathematics. So Hyland discovered the effective topos and proposed it as the world of computable mathematics. So roughly speaking, this is a world where everything is computable and every property is computably satisfied or computably witnessed. Then, so perhaps the most interesting question for computability theorists is, okay, how can we deal with relative computability in the effective topos? So this is a part where the Lawvere-Tierney topologies come into play. So, okay, but the Lawvere-Tierney topology has nothing to do with topology in the sense of topological spaces. So Lawvere-Tierney topology is a generalization of a Grothendieck topology. So sometimes a Lawvere-Tierney topology is also called a local operator or geometric modality. And basically, so historically, a Lawvere-Tierney topology is introduced as a generalization of a Grothendieck topology. And indeed, if we only consider Grothendieck topology, then it essentially coincides with a Grothendieck topology. But an important aspect of such a topology is that if the collection of sheaves with respect to the topology again becomes the topos, which is a subtopos of the base topos. So anyway, the definition of a Lawvere-Tierney topology is slightly technical, so the definition will be delayed to a later slide. Here, the idea of how to understand a Lawvere-Tierney topology is more important than the definition itself. Anyway, it's difficult to get a computability theoretic idea from a formal definition. So at this time, the formal definitions are not so important at all. So first, let's introduce concrete examples of Lawvere-Tierney topologies. So the largest Lawvere-Tierney topology is a kind of indiscrete topology or trivial topology that contracts all truth values to a single value. And so everything is true in the resulting degenerated topos. So it may be thought of as the world of inconsistent mathematics. So the second largest topology is the double negation. So this is a Lawvere-Tierney topology, which has the effect of changing a topos into a Boolean topos. So in the effective topos, the new topos created from the Lawvere-Tierney topology, from the double negation topology is exactly the world of set theoretic mathematics. I mean, it's equivalent to the set of sets. The least topology is the identity topology that does not cause any change to the base topos. So in summary, the trivial topology corresponds to inconsistent. The least topology, the double negation topology corresponds to a set theory, and the identity topology corresponds to a computability theory. So what this suggests is that analyzing the intermediate topologies between the identity and double negation on the effective topos may correspond to exploring the intermediate worlds between computable world and the set theoretic world, set theoretic mathematics. So this is a basic idea of this talk. Okay, so this idea connects the degree theory and the topos theory. And Lawvere-Tierney topology on the effective topos is a kind of data that indicate how much non-computability to add to the world. In other words, Lawvere-Tierney topology plays the same role as an oracle. So originally, Lawvere-Tierney topology is just a generalization of a Grothendieck topology, but from the computability theoretic perspective, surprisingly, one can think of this as an oracle. Yeah, actually, Highland built Lawvere-Tierney topology in this way. So Highland found the topology on the effective topos for each Turing degree D, which indicates a topos that corresponds, which induces a topos that corresponds to the world of the relative computable mathematics. So in this world, everything is computable from the oracle D, and every property is witnessed in a D-computable manner. So we call topology obtained from a Turing degree topology. So I said that Lawvere-Tierney topology is like an oracle. Then, okay, so the question is whether there's a one-to-one correspondence between Lawvere-Tierney topologies and Turing degrees. Unfortunately, that's not so convenient. So there are a lot of Lawvere-Tierney topologies which do not correspond to Turing degrees. So later, Pitts found topology on the effective topos, which is not equivalent to any Turing degree topology. So as for the question of how much Pitts topology differs from Turing degrees, first, Lawvere-Tierney topology can be ordered by its coarseness or fineness. So if we think about Lawvere-Tierney topology as an oracle, then a larger topology in this order is more powerful as an oracle. So in other words, it's an order in the same sense as the degree theory. So this Pitts topology is intermediate between the identity and the double negation. So this topology adds some non-computability. But interestingly, Pitts topology is not bounded by any Turing degree topology. So it's kind of an oracle, but far from any Turing oracle. So, okay, so yeah, anyways, what I want to say is that the study of Lawvere-Tierney topology is basically the degree theory. So in other words, it's an area that deserves more attention from computability theorists. And and actually, so it's, maybe any computability theorist would find interesting. Okay, so then the question is whether there are any open problems about the structure of Lawvere-Tierney topologies. Yeah, of course, there are a lot. So for example, in 2011, Lee asked this question. So does there exist the least Lawvere-Tierney topology on the effective topos strictly above the identity topology? So this is quite a degree theoretic question. So basically, it asks the existence of a minimal degree. To be more precise, it's not about a minimal degree, but the second smallest degree. So it's a stronger statement, but anyway, the type of question often asked in degree theory are also asked in the study of Lawvere-Tierney topologies. So this is just a degree theory. Okay, but the difficulty with problems asking about minimal degrees is that in order to solve it, we have to figure out whole overall structure, what the Lawvere-Tierney topologies are. This is, so here, this is some phrase in Lee van Oosten's paper. So a Lawvere-Tierney, so as I said before, a Lawvere-Tierney topology is also called a local operator or a geometric modality. And so this is some paragraph from Lee and van Oosten's paper. So whereas local operator subtoposes of Grothendieck toposes can be neatly described in terms of Grothendieck topologies, for realizability toposes, the study of local operators is not so easy. The lattice of local operators in the effective topos is vast and notoriously difficult to study. So they say that the lattice structure or frame structure of Lawvere-Tierney topologies is too vast and complicated. So for example, they had no idea how to solve this Lee's question. However, interestingly, Lee and van Oosten have created a very useful tool, even though they couldn't solve this problem. Lee and van Oosten gave a concrete presentation of all topologies on the effective topos. So I don't know if Lee and van Oosten were aware of this, but the tools are concrete and allows us to bring the argument of Lawvere-Tierney topologies into the pure degree theory. So degree theorists know best how to use the tool invented by Lee and van Oosten. So for example, actually by using this tool, we can solve this Lee's question. Okay, so before going to give a proof, I will give an idea how we can study Lawvere-Tierney topologies on the effective topos in the degree theoretic context. So as I said before, a Lawvere-Tierney topology plays the same role as an oracle. And thanks to Highland, we know that each Turing degree is a topology, Lawvere-Tierney topology. Of course, each Turing degree comes from a subset of the natural numbers or a total function on the natural numbers, but many other things can be considered as oracles. For example, one can use a partial function on the natural numbers as an oracle. Actually, a partial function on the natural numbers also is a Lawvere-Tierney topology. So not only Turing degrees, but also enumeration degrees are thought of as Lawvere-Tierney topologies. Not only that, but even a partial multivariate function on the natural numbers can be used as an oracle and has a corresponding topology on the effective topos. So this is the reason why I mentioned Bayer of degrees at first. Actually it's not a Bayer of degrees exactly, but the generalized Bayer of degrees. Anyway, this is a very familiar concept to the Bayer community and one that they are very comfortable with. Okay, so let's introduce the notion of computation relative to a partial multifunction on the natural numbers. Our model is the same as that of an ordinary programming language with oracles or oracle Turing machines. So there is a special instruction to read a single bit of an oracle. So the program P accepts a number n as input and a partial multifunction on the natural numbers as oracle. And this special instruction assigns one of the values to the variable b, one of the values of FA to the variable b. However, if FA is undefined, the computation will never terminate. And if F is multivariate, this generally produces a non-deterministic computation. So if the non-deterministic computation terminates on all the paths, the result of one of the paths is one of the outputs. So since there are multiple paths of the non-deterministic computation, this computation generally gives a multivariate function. So it's simply an extension of the usual notion of oracle computation to multivariate functions. And of course, if you have heard about the generalized Bayer of degrees, reducibility, yeah, it's exactly the natural number version of the generalized by of degrees. But so you don't need to understand it completely here so I will explain more general concepts in more detail later. Okay, so this is the idea of relative computation with respect to partial multifunction. Okay, so the consequence of this observation is that there exists an embedding of the natural number version of the generalized by of degrees into the lattice of Lawvere-Tierney topologies on the effective topos. Anyway, in general, this embedding result holds for most of relative realizability toposes. So, for example, if we consider the clean Bessel topos, this embedding results says that the generalized by of degrees in the usual sense embed into the lattice of Lawvere-Tierney topologies on the clean Bessel topos. So, based on this idea, it's possible to position the study of the structure of Lawvere-Tierney topologies on relative realizability toposes as an extension of the study of the bi-life lattice or the bi-life style reverse mathematics. Maybe based on this idea, so we can establish something like topos theoretic reverse mathematics or something like this. So this is not completely finished yet, but I'm considering on about it. So for example, the internal logic of sheaf topos with respect to Lawvere-Tierney topology on realizability topos can be expressed using something like Lifshitz-like realizability in incorporating Lawvere-Tierney topology. So yeah, this can be translated into a realizability that incorporates by of degree, and what is happening in the internal logic of the sheaf topos can be controlled to some extent by of degree. So using this, for example, it's possible to show separation results on constructive reverse mathematics over IZF, intuitionistic ZF set theory using by of degrees. Anyway, so unfortunately, this is just an embedding, and it's not an isomorphism. So this does not characterize the whole structure of Lawvere-Tierney topologies. But this suggests that there are other kinds of oracles which cannot be described as partial multifunctions. So for example, if we want to solve this question, we need to know what the Lawvere-Tierney topology is, what is allowed as an oracle. Okay, so one of the main observations in this talk is that every Lawvere-Tierney topology can be considered as an oracle in a certain sense. Such a general oracle may be out of the scope of generalized by of degrees, but still one can think of it as an oracle. So, okay, in what sense it is an oracle? Okay, so to explain this, we give an example of a Lawvere-Tierney topology which lies outside of generalized by of degrees. One example comes from a probabilistic computation. As a simple example, let's consider the situation where a program P is given an oracle alpha at random, and for an input n, the oracle computation P alpha n holds with probability at least 1 minus epsilon. In other words, this is a situation where the measure of A is at least 1 minus epsilon, and the computation holds for any random oracle from A. So this probabilistic computation is a multifunction such that the result of the computation P alpha n for each random oracle alpha from A is a possible output. So several people have considered probabilistic computation in the viral context. So I believe you can see that it's clear that this is a partial multifunction. Anyway, this partial multifunction has two parameters. N and A. Of course, N is an input given by us, while A is a witness that the computation holds except for probability at most epsilon. It's only guaranteed that such an A exists mathematically, but the computer does not know what exactly A is. So let's write prob error epsilon p for this procedure of giving an oracle randomly to the program P and having it perform a computation with error probability at most epsilon. So if one wants to make explicit a parameter A, which witnesses the computation succeeds with error probability at most epsilon for input N, we use the notation prob error epsilon Pn by A. So a pair N by A of parameters is properly accepted only if A witnesses that P alpha N holds except for probability at most epsilon. Then the value P alpha N for each alpha in A is a possible output. Of course, also the roles of N and A are entirely different. If we just treat them formally, the above process can be regarded as a partial multifunction of this type. So this type. The A is the witness of termination of the computation on a sufficient measure. So mathematically, N and A are both considered to be inputs, but computationally, they have completely different roles. Okay, so in this sense, both N and A can be thought of as inputs for the above multifunction, but N is an input that is disclosed during the computation, while A is an unknown input that cannot be accessed during the computation. So we call N a public input and A secret input. So this has two kinds of inputs. In the context of computation, a public input is an input which we give, and a secret input is a witness of something which we do not know at all during the computation. So we will call LT problem a function that takes public input and secret input as inputs. A public input is a natural number, but a secret input can be anything. For example, in the previous example of probabilistic computation, a secret input was a subset of control space with a large measure. We write input for G as N by C, where N is a public input and C is a secret input. Okay, so what does it mean to use an LT problem as an oracle? A secret input for an oracle acts like an advice string, which is usually used to define non-uniform complexity classes in computational complexity theory. So in general, an advice string yields non-uniformity, and it's a secret input in this context. Okay, I'll give an example. Of course, the previous probabilistic computation is an LT problem. Also, any partial multifunction can be thought of as the LT problem with no secret input. The secret input part is trivial. Some LT problem has exactly the opposite properties. It is an LT problem with no public input. So this is an example which an example is this the natural number advice function advice n. So advice public input is trivial, and it has a secret input which is a natural number. And this notion is actually studied in computable analysis in about 10 years ago to characterize non-uniform computability. Yeah, in type 2 theory of effectivity, a function is non-uniformly computable if and only if it is computable with the help of the natural number advice. So this is the reason why I said that the secret input for an oracle acts like an advice string. Okay, so there are a number of non-trivial natural examples of LT problems, the probabilistic computation or the random advice, the natural number advice, and so on. Actually, in the type 2 theory of effectivity, there are many studies on computation with advices. So in particular, one query relative computation with advices, for example, by Martin Ziegler, Vasco Bratka, Arno Pori, and others. Yeah, similarly, the notion of encodability and omniscience reducibility used around computability and reverse mathematics on Ramsey's theorems are also related to this notion. These concepts transform information that is normally treated as public information into computationally inaccessible secret information and analyze the resulting computational strengths. So it's a well-studied concept in some sense. There is also another coincidence. So surprisingly, one query relative computation for LT problems has been studied by Andrew Bauer, who recently introduced the notion of extended Bayer reducibility. So yeah, actually, it's not recent, but so Bauer recently wrote a new paper on extended Bayer reducibility, which is different from the old version of extended Bayer reducibility. So the new version is much wider concept than the old definition. Okay, so so in this sense, this is a well-studied concept, but all of them are about one query reducibility. So we need many query relative computation with advices. So one query version is basically something like Bayer reducibility, and many query version is generalized Bayer reducibility. And Bayer reducibility for the LT problem is extended Bayer reducibility. So many query relative computation with advices would be called generalized extended Bayer reducibility or something like this. But the name is too long, so I would call it LT reducibility. Okay, so this is an idea of many query relative computation model. So I will give a rough idea of the definition here and give a more detailed definition in the next slide. Okay, so this is a rough idea of our many query relative computation model. Okay, so during a computation with an LT problem oracle F, when the program makes a query N to F, the advisor who has non-computable power chooses the parameter C. This is a secret input. So the information of C chosen by the advisor is not given to the machine. So C is a secret input or a secret advice or something, but only the information of one of the possible values of Fn bar C is given to a machine. So as before, this gives a non-deterministic computation. If this process computes a partial multifunction G, when the advisor secretly makes the best choice, then we declare that G is LT reducible to F, or maybe G is generalized extended Bayer reducible to G, F. So this is our computation model. Okay, so now surprisingly, this characterizes the Lawvere-Tierney topologies. The structure of LT degrees, this notion of LT problems, is isomorphic to the lattice of Lawvere-Tierney topologies on the effective topos. So this LT reducibility notion completely characterizes the notion of Lawvere-Tierney topologies. Actually, we can get the same result for Kleene-Bessel topos or its relative. Yeah, this actually has almost been proven by Lee and Van Osten. they gave some characterization of Lawvere-Tierney topologies on the effective topos. And what this comment means that we can show that the Lee and Van Osten's characterization is equivalent to our Lawvere-Tierney reducibility characterizations. Okay, so Aaron gave a question. Can the advisor make a new choice for each? Yes, the advisor can make a new choice for each query. Yeah, actually, yeah, I will give the more detailed definition in the next slide. So I will explain in the next slide. Okay. Anyway, so this computability theoretic reducibility notion characterizes the lattice of Lawvere-Tierney topologies on the effective topos. Okay, so now I give the formal definition of LT reducibility. So it's quite similar to generalized Bayer reducibility. The definition of LT reducibility can be understood by describing it as an imperfect information game between three players. So I will call these players Martin, Arthur, and Nimue. So yeah, this is because in complexity theory, there is something called Arthur-Martin protocols, which is used when the computational powers of two players are completely different. In our case, Martin can do any uncomputable things, but Arthur can only do computable things. Also, there is the third player, Nimue, which plays the role of a secret advisor. So this is basically a generalized Bayer reduction game, but with secret moves. So first, the player Martin makes a public input x0 and a secret input c0 on his first move. So here, among the moves of Martin, only the secret input c0 is invisible to Arthur. Green symbols are public moves, which Arthur can see. And blue symbols are secret moves, which Arthur cannot see. So Arthur is basically machine, and Nimue is the advisor. And green symbols are public moves. Blue symbols are secret moves. So all of Nimue's moves are visible to, Martin can see both public moves and secret moves, but Arthur can only see public moves. Nimue can see all moves. So all of Nimue's moves are visible to Martin, but not to Arthur. And most of Martin's moves are public moves except for C0. So this is a basic convention for our game. And the remain is the same as generalized Bayer reduction game. Okay, so first, Martin chooses public and secret input for, so we define the reduction game for F. So F is LT reducible to G. Okay, so first, Martin chooses the public and secret moves for F. And at the nth round, Arthur reacts with a pair. The first coordinate of Arthur's move codes whether to stop the computation or to still continue the computation. If the first coordinate is 0, then the computation does not hold at this round. And then Arthur makes a new query, UN to G. If the first coordinate is 1, then the computation holds at this round. And Arthur declares termination of the game with UN. So Asa wins if UN is a correct output for f x0 bar c0. If Asa decided to continue the game, the next Nimue secretly makes an advice parameter Zn, which is contained in the domain. At the next round, Marin responds to the query made by Asa and Nimue at the previous stage. This means that xn plus 1 must be a correct output for gun bar zn. So this is our reduction game. Okay, so Asa and Nimue win this game if either Marin violates the rule before Asa or Nimue violates the rule, or both Asa and Nimue obeys the rule and Asa declares termination with a correct output for f. That is, Asa correctly succeeded to calculate an output for fx0 bar c0. So Asa can only read the public moves x0, x1, x2, and so on. And the other players can see all the moves, as I said before. So Asa's strategy is a partial function from finite string to the natural numbers, which reads Marin's public moves and then returns the nth move. Then we say that f is LT reducible to G if there exists a pair of Asa's computable strategy and Nimue's strategy, which is not necessarily computable, which is winning for this reduction game for that f is LT reducible to G. Yes, this is exactly a generalized Bayer reduction game, except for the existence of secret moves. So Lee and Van Osten actually characterized Lawvere-Tierney topologies by something they called dedicated site, but the terminology is very, very different. But one can show that a dedicated site is essentially the same as this. But their description, Lee and Van Osten's description, is neither game theoretic nor computability theoretic. Okay, so now, so this is a definition. So this is our reduction game. Okay, so next, this is the definition of Lawvere-Tierney topology. So yeah, this is a topos theoretic notion. So let E be a topos with a sub-object classifier. So true from the terminal object to the truth value object. In the effective topos, truth value is a subset of natural numbers, basically. So true corresponds to the whole natural numbers, and false corresponds to the empty set. So the truth value object is basically the power set of the natural numbers. So a Lawvere-Tierney topology on the effective topos, a Lawvere-Tierney topology on the topos is a morphism on the truth value object satisfying this property. So the first one says that if something is true with no help, then it is true with the help of J. The second one says that J preserves conjunction. The third one says that J is idempotent. Okay, then how can we construct a Lawvere-Tierney topology from a LT problem? We need to make an operator on the truth value object. So given an LT problem G, we define G arrow in this way. So if a truth value P is given, then an output for G arrow is an index of Asa's computable winning strategy, solving P from G. this is the Lawvere-Tierney topology because first, if one can solve the problem P without any help, it is clear that one can also solve the problem with the help of G. So yeah, this is a very rough proof, but second, if one can solve problems P and Q with the help of G, then by running these strategies in parallel, one can also solve the conjunction of P and Q with the help of G. And the last condition follows from transitivity of LT reducibility. So yeah, we can actually show that the LT reducibility is transitive as as in the proof of transitivity of generalized Bayer reducibility. Okay, so in this way, so we can make a Lawvere-Tierney topology, and conversely, so from a Lawvere-Tierney topology, we can construct a LT problem. But it's a bit technical. So yeah, so maybe I think I don't have enough time to give the detail of the proofs. But anyway, in some way, we can show that the structure of Lawvere-Tierney LT degrees of LT problems is isomorphic to the lattice of Lawvere-Tierney topologies on the effective topos. So, so rather than the proof, I would rather talk about applications of applications to specific things than generalities. So let me be specific. So I would discuss about the specific Lawvere-Tierney topologies. So, anyway, so the important point is that, so we can characterize the structure of Lawvere-Tierney topologies by using the LT reducibility notion. Okay, so after we get this characterization, so we can just use some kind of Bayer reducibility to study Lawvere-Tierney topologies. Now, for computability theorists, it's very easy to deal with Lawvere-Tierney topologies. This is because it now becomes the degree theory. So now we can get a lot of results about Lawvere-Tierney topologies. I will give some examples of LT problems. The first LT problem is error M over K. This is a problem such that M of the K choices are wrong. In particular, one query error M over K relative computation is the one in which K computations are run in parallel, M of which may be wrong. So this error has no public input. It only has a secret input. Yeah, of course, this is closely related to the well-studied notion, the lesser limited principle of omniscience, LLPO. But this is the natural number version of LLPO. So in the case of LLPO M over K, we also see that at most M of the K choices are wrong. However, in the case of LLPO, the information about which is wrong is given in a CE way, computably enumerable way. In the case of error, no computational information is given as to which is wrong. So, yeah, the point to be noted here is that for any virus problem, a new LT problem can be created by changing the public input to secret input. For example, this error is an LT problem obtained by changing the public input of LLPO to secret input. So, yeah, of course, error is stronger than LLPO relative to any oracle. And actually, we can show that LLPO M over K is LT reducible to error M over K plus 1, but LLPO M over K is not LT reducible to error M over K plus 2. And LLPO M over K relative to the halting problem is not LT reducible to error M over K plus 1. Okay, so now the goal of Lee and Van Osten was to find many concrete Lawvere-Tierney topologies different from Turing degree topologies. Lee and Van Osten used this error problem to show that there are infinitely many basic non-Turing Lawvere-Tierney topologies. Now, as mentioned earlier, we know that we can create a LT problem from any Bialov problem. However, Lee and Van Osten, maybe Lee and Van Osten probably did not know Bialov degrees, so they could only find a concrete non-Turing Lawvere-Tierney topologies in the form of error. So for this reason, Lee and Van Osten asked what the structure of error was. However, Lee and Van Osten's question can be easily solved by using previous degree theoretic results. So yeah, at least we could solve one problem in a degree theoretic way. Okay, I don't explain the details. So this is very technical. So okay, but basically most of the idea comes from Senzer-Himmel's result on Medvedev degrees. Okay, so and also Lee and Van Osten also discussed about error 1 over omega. This is a problem such that one of the omega choices are wrong. And interestingly, Lee and Van Osten showed that error 1 over omega is the least basic Lawvere-LT problem, which is strictly so LT above the identity. So Lee and Van Osten stated this theorem in the context of Lawvere-Tierney topology, but in our context, Lee and Van Osten's result can be restated as this. Here, LT problem is basic if it has no public input. So error 1 omega is the least basic LT problem, which has no public input. So in some sense, this is minimal. So, but of course, it's not the least among all LT problem, which is strictly above the identity. So, yeah, because, for example, this is a modest version of, so as a modest version of this error 1 over omega is studied as all or co-unique choice. And so all or co-unique choice is defined like this. And yeah, clearly error 1 over omega is stronger than all or co-unique choice relative to any oracle. So error 1 over omega is not a minimal degree. So for this reason, Lee asked about a minimal Lawvere-Tierney topology on the effective topos. I mean, asked about the least Lawvere-Tierney topology on the effective topos strictly above the identity topology. Okay, so, and but as a benefit of bringing the argument on LT topologies in the degree theoretic context, we can solve this problem. And the answer is no. There's no minimal LT problem. Yeah, actually, LT degrees is lower dense, downward dense. Yeah, actually, the proof is easy just by a simple forcing argument. So it could be solved by any degree theorist. Okay, so this is a picture of the lower part of the frame structure of Lawvere-Tierney topologies on the effective topos, or one could say the lower part of the LT degree structure. Here the term modest is Andre Bauer's terminology, but it originally from realizability theory, but also used here in a slightly different sense. So roughly speaking, modest ones correspond to Bayer problems. So yeah, modest topology is exactly Bayer problems. And non-modest ones correspond to non-Bayer LT problems. So in other words, non-modest ones involve secret inputs. So I will give other example about LT problems. The non-modest LT problems we have dealt with so far was of no help at all for computing a single valid function when treated as an oracle. However, indeed, there is a non-modest LT problem which is rather powerful when considered as an oracle. So Pitts introduced the non-modest LT problem, cofinite. So yeah, basically one query cofinite relative computation is the one in which countably many computations are run in parallel, a finite number of which may be wrong. So interestingly, Van Osten showed that for a total function on the natural numbers, Pitts topology forces F to be decidable if and only if F is a hyperarithmetic. In our terminology, Van Osten theorem can be stated as this. So a total function F is hyperarithmetic if and only if F is LT reducible to cofinite. So of course, this theorem is related to Lawvere's result on encodability related to Ramsey's theorem. So in fact, encodability and omniscience reducibility are closely related to LT computation with secret input. Okay, so as a candidate for another non-modest LT problem, so one that uses a lower asymptotic density may come to mind. So this corresponds to the world of computable mathematics with error density epsilon. And we can show like something like this. So cofinite is, so this is a lower asymptotic density. And so then error epsilon accepts only secret inputs when the lower density of the secret input is at least 1 minus epsilon. And then the output of the error epsilon is just any element from the secret input. Then we can show that cofinite is LT reducible to then error epsilon, and error 1 over L is LT reducible to then error 1 over L. And also we can show something like this. So let P be a partial multifunction whose codomain is finite. Then for any epsilon less than 1 over L plus 1, if P is hyperarithmetical LT reducible to then error epsilon, then P is hyperarithmetic. So then error does not add the hyperarithmetical power if the codomain is finite. So as a corollary, so F is hyperarithmetic if and only if. So F is LT reducible to then error epsilon for if epsilon is less than half. And pi 1 LLPO 1 over L is hyperarithmetically LT reducible to then error 1 over L plus 1. And pi 1 LLPO 1 over L is not hyperarithmetic LT reducible to then error 1 over L plus 2. And we can also show that cofinite is strictly LT below then error 0. So we have this kind of hierarchy. And also, of course, this is the Lawvere-Tierney topology. So this notion is different Lawvere-Tierney topologies, and so this is different subtoposes of the effective topos. Okay, so this is a picture of the higher parts of Lawvere-Tierney topologies on the effective topos. So it's something like this. Okay, so in this way, we reduce the problem of Lawvere-Tierney topology to the problem of Bayer degrees in computable analysis. In an abstract setting, it's very difficult to reveal a concrete structure and solve a concrete problem. So being able to reduce an abstract problem to a concrete one in this way is very significant. So, okay, anyway, so by using this, I was able to give solutions to all the problems mentioned in Lee and Lee Faunstein's paper. So, and okay, one of my future plans is to apply this idea to constructive reverse mathematics, as I mentioned earlier. So, okay, so one of the new things that we have learned by relating Bayer degrees to topos theory is that Bayer degrees is not only related to reverse mathematics on constructive second-order arithmetic or such as Troestra's EL node, but also to reverse mathematics on constructive or intuitionistic set theory. So through this method, we can get many separation results on reverse mathematics over CZF or IZF, so I mean constructive set theory or intuitionistic set theory, by using Bayer degrees or generalization, so extended generalized Bayer degrees. So this is the direction I'm currently working on. So yeah, well, I hope it will help to expand the scope of reverse mathematics. Okay, so that's all. Thank you for your kind attention.